Hello everyone, we are from Group 11 and today we will be presenting on design of reactor separator system for methanol production plant. Before we begin, I would like to introduce our team. Our group consists of 6 people, which are Fatin, me, myself, Diane, Qayyum, Farhan, Nivanat and also Lashwin.
Hi. Today I will be presenting the executive summary part of our integrated design project on methanol synthesis. So this project focuses on the production of methanol using the conventional syngas based route, where carbon monoxide and hydrogen react in the presence of a catalyst. Methanol is an important industrial chemical widely used in fuels, solvents and chemical manufacturing. In the reaction engineering part, methanol is produced through catalytic hydrogenation using copper or zinc oxide or aluminum oxide. Catalyst in a plug flow reactor. So the reactor operates at high pressure and moderate temperature to achieve optimal conversion and efficiency. For the separation process, the reactor effluent is purified through condensation and distillation to obtain high purity methanol. Unreacted gases are recycled back into the reactor to enhance overall efficiency and to reduce the waste. So process optimization is also considered by analyzing key parameters such as temperature, pressure and feed composition to improve methanol yield and ensure stable reactor performances. So in conclusion, this integrated design project provides an efficient and industrially feasible approach for methanol production with high conversion, improved purity, and optimized performance. Thank you.
Methanol synthesis is the catalytic conversion of syngas, which contains carbon monoxide, carbon dioxide, and hydrogen into methanol. The main reaction is the hydrogenation of carbon monoxide to form methanol, while the water gas shift reaction produces additional hydrogen for the process. A copper, zinc oxide, or aluminum oxide catalyst is used to enhance reaction rate and improve selectivity. The process starts with syngas production, followed by compression and heating. The mixture then enters the reactor where methanol is formed and finally goes through separation to obtain the final product. Methanol synthesis occurs via heterogeneous catalysis, where reactants are first adsorbed onto the catalyst surface, undergo the reaction, and then dissolve as products. The reaction is exothermic, so strict temperature control is essential. The water gas shift reaction helps improve the hydrogen to carbon monoxide ratio, enhancing methanol yield. Typical operating conditions are 200 to 300 degrees Celsius, with an optimum around 250 degrees Celsius, and pressures between 50 and 100 bar to favor methanol formation. A hydrogen-rich feed also improves yield and prevents catalyst deactivation. Overall, efficient methanol production requires a careful balance of kinetic, thermodynamics, and catalyst performance.
In methanol production, the reactor effluent is a complex mixture of methanol, unreacted gases like hydrogen, carbon monoxide, carbon dioxide, and water. Because of this, an efficient separation system is required to recover high purity methanol while minimizing losses and improves overall efficiency. The separation process relies heavily on the fundamental concept of differences in physical properties between components. In our case, we primarily exploit differences in boiling points and adsorption affinities. The feed stream first enters a distillation column where the principle of vapor-liquid equilibrium is used. Components with lower boiling points rise to the top as vapor, while higher boiling components remain in the liquid at the bottom. This allows an initial separation of methanol from other gaseous and liquid impurities. From the distillation column, the overhead stream is sent to an adsorber, which removes remaining impurities based on adsorption process. The adsorbent material selectively retains water or other contaminants, leaving purified methanol. The bottom stream goes to a component splitter where the remaining methanol is separated from purged water using further phase separation or distillation principles. This integrated design demonstrates key chemical engineering separation principles. By combining these steps, we maximize methanol recovery, reduce waste, and improve overall energy and material efficiency.
Assalamu alaikum and hi to respected lecturers. I am Abdul Shah and I will be presenting the reactor system that we chose for this project. For methanol production, the conventional CO-based syngas route is selected. This route has been widely used in the industry since the 1960s and is a proven reliable technology. It is less energy intensive compared to alternative routes and benefits from high technological maturity, ensuring consistent and efficient production. Additionally, Malaysia has abundant natural gas resources, making the CO-based syngas route particularly suitable. This route also offers low energy requirements and production costs, making it economically attractive. For the reactor design, several assumptions are made to simplify modeling. The system is treated as a plug flow reactor with ideal plug flow behavior and isothermal operation, meaning that the constant temperature is applied in this case. The gas is assumed to behave ideally with constant physical properties, negligible pressure drop, and constant catalyst activity. Reaction kinetics are a key factor in a reactor modeling and simulation. The methanol synthesis rate depends primarily on the concentration of carbon monoxide and hydrogen gas and follows the Arrhenius equation. The activation energy for methanol is approximately 95,000 kilojoules per kilomole, while the water-gas shift reaction has an activation energy of around 67,000 kilojoules per kilomole. These kinetics are essential for predicting reactor performance and optimizing operating conditions. The material balance for the methanol synthesis process was evaluated under typical operating conditions of 250 degrees Celsius, 50 bars, and a feed rate of 1000 kilomoles per hour. Process produces for approximately 283.55 kilomoles per hour of methanol. As expected from the reaction stoichiometry, the total molar flow of the system decreases due to the conversion of reactants into products. However, mass is conserved throughout the system, confirming that the process is at steady state. From the performance, we can conclude that it indicates high efficiency and effective syngas utilization. Elemental balance was also performed to validate the simulation accuracy. The carbon balance is 100.1%, hydrogen is 99.5%, and oxygen is 100.1%. These results demonstrate both mass conservation and the reliability of the simulation model, ensuring that the process design and calculations are accurate and consistent. For methanol synthesis, a packed bed reactor or PBR is selected as and modeled as a plug flow reactor. This type of reactor offers several advantages, including high conversion efficiency, effective catalyst utilization, and suitability for continuous gas phase reactions, which makes it ideal for industrial methanol production. The reactor operates within a temperature range of 200 to 300 degrees Celsius, with an optimum around 250 degrees Celsius, and at pressures between 50 to 100 bar. The feed ratio of hydrogen to carbon monoxide is maintained at 2 to maximize methanol formation. These operating conditions ensure high conversion and selectivity, allowing for controlled reaction progression while minimizing side reactions. Overall, the packed bed reactor provides an efficient and reliable platform for methanol production in a continuous
Good
process.
evening, I'm Nivnat and I'll be talking about the separator part of a methanol synthesis system. First off, in our system, we have methanol, water, carbon monoxide, and carbon dioxide. However, water is the main byproduct, primarily formed through the hydrogenation of carbon dioxide. And our strategy to achieve the purification efficiency is to conduct the synthesis at 25 to 60 degrees Celsius at atmospheric pressure with a downward flow. And for our process, firstly, we have condensation, where the effluent is cooled to separate liquid from gases. We also have a primary adsorption, where 3A molecular sieves are used to remove water while excluding methanol based on their kinetic diameter. Next, we have a secondary adsorption, where we are using activated carbon to remove any trace of dissolved gases and silica gel for final water polishing. Lastly, we have regeneration, where we are utilizing a duty or standby configuration with temperature swing adsorption to ensure continuous operation. Next, I'll be talking about the adsorbent selection as well as the column design. For the adsorbent, we are using a 3A molecular sieves with high selectivity and thermally stable. We are also using activated carbon, which has a high surface area, especially for non-polar or weakly polar trace impurities. For the isotope models, we are using a Langmuir model, especially for water on molecular sieves, and this assumes monolayer adsorption on homogeneous surfaces with a defined saturation. For the Freundlich model, it is used for trace gases on activated carbon, and this accounts for heterogeneous surfaces and multilayer adsorption without a defined saturation point. For our design calculations, the calculated mass transfer zone for water adsorption is 0.032 meter, and this small value indicates a highly efficient adsorption utilization. As for the inventory estimation, the system water mass flow rate is 1973.75 kg per hour, and this causes each column to require approximately 132,870 kg of 3A molecular sieves.
Hi, I'm Farhan, and I'm going to talk about the conclusion for our report. First of all, we choose a conventional syngas rod using natural gas because it is a proven technology with a low risk and it is very suitable in Malaysia. Secondly, we selected PFR, which is known as a plug flow reactor, since it works well for continuous gas phase reaction. And for the catalyst, we use copper, zinc oxide, and aluminum oxide. Third, the best operating condition that we found are at 250 degrees Celsius, and for the pressure, it is at 50 bar. Under this condition, we get high conversion of carbon monoxide, carbon dioxide, and hydrogen, methanol yield of more than 85%, and almost 100% of selectivity, which means very little of unwanted product is formed. Fourth, our simulation results are very accurate because both the material and elemental balance are well close. And finally, for a future improvement, we suggest developing a better catalyst to improve the performance and adding a better heat integration to save energy. In short, our design is practical, reliable, and well suited in Malaysia. Thank you. I think that's all from Group 11. Thank you.